Okay, so this is the second part of the video for the lecture on Wednesday, November 29th. We are continuing on from where we were before. We started off with visualizing the data. We visualized it in space, we visualized it in time. Then we did some animation to try and capture that space-time behavior. So let me jump to here. So that's what we've done, is kind of up through here. Next is to do exploratory data analysis. And what we really want to do is we want to understand the space-time variogram. So you can follow along in Schabenberger and Gotway in section 9.4. This also appears in the Spatial Statistics with R book in section 2.4.2. So we want to estimate the variogram at different space and time lags. And as we know from just the spatial piece, we need to take care of the mean component before we try and describe dependence, before we try to describe covariance or the variogram. And extracting the mean is challenging. It can often be difficult to decide what you want to build into the mean and what you want to leave in for the covariance structure to describe. But if we think about our temperature data, I think there's some stuff that naturally makes sense to build into the mean. When we investigated the temporal behavior of our data, we saw that temperatures were tended to be highest in the middle of the summer and lower at the beginning and the end of the summer. That's not a surprise. We would probably want to build that into our mean structure. We also saw that temperatures were higher in the south than in the north, and so we'd probably build that into the mean structure. If we can estimate those pieces of the mean, subtract them off, get some residuals, then we would try to build dependence in those residuals. So let me just show that really quickly in R. Okay, so I have my Tmax data here. So you can ignore this column of residuals. That's left over from before. The Tmax data that we left off ended with column T. This column of residuals is going to appear after I subtract off the mean. And so you can see here in line 120, what I'm going to do is I'm going to fit a linear model where our temperatures Z are a function of latitude. So we're going to build that north to south. And then are also functions of time and time squared. So the time squared is because we saw the temperature increasing and then decreasing. And so fitting a quadratic model in time, it might be rather crude, but would kind of take care of that. So here is our fitted linear model. If we get the summary stats for this, we see that it is showing that all three of our regression parameters are strongly significant. So it's saying, yeah, include those. We would want to check, and then what we want to do is we want to check the residuals and see if it seems like we've captured that. And so we could do the same sort of investigation that we did before, where we look at individual time series at individual locations. We could look at spatial maps. We could even do an animation. Here I'm in line 122, I'm going to create that column of residuals. And so this is from taking our temperatures and then accounting for the mean as we did up there in line 120. Here in line 126, and so I'm just going to make a similar plot to what we did before. This is just going to be looking at it spatially at 3 different times. I am going to look at it on the first day, the 75th day, which is about midsummer, and the 150th day, which is about the end of the summer. And so by no means is this an exhaustive investigation of these residuals. But we seem to, just looking at these 3 days, we're not seeing that pattern of higher temps in the south than in the north. We're notice that the scale here is ranging from negative 15 to positive 15. And we're not, there's no real indication that there's seasonality here in the residuals. So we could investigate that further using plots and like we did before, but at least as a crude estimate, this seems like a way of accounting for seasonality with the quadratic trend in time and accounting for a north-south gradient in the temperatures. Okay, so after we've accounted for the mean, now we're ready to investigate the space-time covariance structure. And that's where I want to pick up. So if you remember how this worked when we were dealing with just space and not time, we defined the variogram to be 1/2 the expected value of ZS minus ZS plus H squared. That was the variogram at lag H. If it's isotropic, this H is just a scalar of distance rather than direction. If our process is stationary, which if we've accounted for the mean behavior, hopefully we have data that we can assume is stationary. We know that there's a relationship between the variogram and the covariance function. The variogram at lag H is the covariance function at lag 0, or otherwise known as the variance, minus the covariance at lag H. We then said a natural estimator of the variogram is this thing here. Though the 2 on the bottom comes from this 1/2. And then basically we're just taking an average of the squared differences from ZSI and ZSJ, where the distance between location SI and SJ is approximately H. So remember what we did was we binned distances, and then we got our sample, our empirical variogram that gave us points at different binned distances H. And then if we wanted to fit a model to our variogram, we would choose a model. So we could choose exponential or Gaussian or Matern or whatever. And then we had 2 choices, basically. We could fit to our pseudo data to those points via least squares or probably weighted least squares. Or we could fit the original data via maximum likelihood or composite likelihood or something like that. We're going to kind of do something, well, really where we're going to focus in this lecture is number 2 on the estimated variogram. Okay, so the idea is let's extend that approach to the space-time setting. And so we're going to define the spatiotemporal variogram this way. It looks basically the same as before, only now instead of just being arguments of space, now we've got Z as a location in both space and time. The natural estimator is going to be basically the same thing. Take, this is NHK, so take basically the number of observations whose locations are approximately H apart and whose time difference, time lag, is K. And then, so we're going to take all of those pairs that meet these requirements, take the difference, square them, add them up, divide by that number to get our empirical space-time covariagram. So this seems like an obvious definition, but it's because it's an argument of 2 different things, a lag H, and which I'm going to assume is distance. I'm going to assume things are isotropic just to make my life easy, and also a time lag K. So the way I think to picture this is basically imagine we're doing a variogram estimator for different lags K. And so what I'm trying to show in this picture is specific for K equals 0. So what I have, imagine I've got data, I've stacked it up like the way I tend to think of it. And then for K equals 0, what we're looking at is just the data within each slice. And so if H1 is this short lag, this is supposed to be a double arrow. Maybe I've got sets of points whose spatial distance is about that. In my little cartoon example, I've only got one pair of points. But of course, I can estimate that variogram at that lag using all of the different times. And so even if I only had one pair at that distance, at each time I'd have many times to estimate that. So we've got a tremendous amount of data to estimate the variogram at lag 0. If H2 is a little bit longer, maybe I've got this pair and that pair, but of course I can use all of those pairs across time to estimate. And so what we would get is something very familiar to us. We take all of our red pairs and get a red dot. We take all of our green pairs and get a green dot. We get dots for various lags up here. And we would, by eye or something, get a model where the sill seems to level off where the data seems to be leveling off, with an effective range that's approximately right. We could, if we shrunk things down, we could talk about smoothness, but we get an idea of how spatial dependence works at time lag 0. Well, we've only done it for one time lag. We need to do this for time lag 1 and time lag 2. So let's take a look at what that might look like. So here's my picture again. I've got the same points. Here's time 1, time 2, time 3. Let's do the red point first. What we're estimating is gamma hat H time lag 1. So H1 is going to be this short lag, but we're not going to take this pair and combine them anymore. We need to take pairs of points which have a distance about this apart and who are time lag 1 apart. So this point could get paired with that guy because the distance H is about right and we're at time lag 1. This guy could get paired with that guy. And then we could, but of course we don't have to only do between time 1 and time 2. We could do time 2 and time 3, etc. For the green points, we pair up these two guys with their opposite pair, these two guys with their opposite pairs. We could do it between time 1 and time 2 and time 2 and time 3, and we could get the green point. So we got our red point, we got our green point. Notice we can also do at distance 0 now. I can take this point and that point, which are at the same location. I can see I can take Z at this time, I can take Z at this time, I can take their difference, square it, add them up, divide by them. And so we can even estimate at distance 0 with greater time lags. And of course, I've only drawn these blue arrows in for these points, but we could use blue arrows at all of these points to estimate this at time 0. So what we would do is we would get a plot like this for, down here, I should have this labeled with an H, but H is increasing. This is all, these estimates are all at lag 1. And what we would expect to get is something that looks kind of like this. We might see what we would before think of as a nugget effect, but there's going to be some difference between Z at this time and Z at that time. And so when I take the difference, square it, add it up, I'm expecting to get something probably non-zero here. We would think that theoretically it should probably level off at the same height as the sill back here, because remember, the sill is indicating what the variance is. Basically, when points are far enough apart, then there's no shared information between our two Z terms being subtracted. And so points that are far enough apart are going to return on average the same value. And so this sill value should be, we would expect it to be basically the same at lag 0 and lag 1. The effective distance is likely shorter, and I didn't draw that well in this picture, but with a time lag of 1, it probably takes a shorter amount of spatial distance to get effectively uncorrelated data. Of course, we could continue to do this for lag 2 and lag 3. So lag 2 would look something like this. I'd take to estimate gamma hat H1 lag 2. These 2 points are a distance, roughly H1 apart. I'd take this guy with its component-wise guy up here but skipping, of course, time equals 2. I could take lagged observations 1 and 3, 2 and 4, 3 and 5, etc. Okay, so what we have now, in your mind, hopefully, is a picture that looks like this for every lag. I've got it for lag 0, I've got it for lag 1, I've got it for lag 2. And what we'd like to do is put that into one picture. And how can we combine all that information into one picture? Well, the idea is something like this. Think of a variogram plot where we have our lag H in the horizontal direction as we have before. But instead of having gamma hat on our vertical axis, what we're going to have is K, the time lag. And then what we would have coming out of this, would be, think of the height leaving the paper as our variogram estimate. So this, unfortunately, it's rather small, but what I'm trying to show here is this is gamma hat H1 lag 0. This would be gamma hat H2 lag 0. Here's gamma hat H1 lag 1, gamma hat H2 lag 1. And of course, we can't really plot it coming out of the paper in 3 dimensions, but what we could do is give it different colors, and like we've done a number of times, and those colors would indicate what that level of dependence is being given by the variogram. So that's the idea I want you to have for a space-time variogram. Let's jump to R and let's see how Weichel and Zamet-Manjian and Cressy do this. Okay, so you're seeing my R screen again. It would be nice, we extracted the residuals, and it would be nice to apply this to the residuals, and we'd have to format the residuals in a way that would work with the R tool, and I haven't had time to do that. So we're going to switch data sets ever so slightly. I'm going to read in this data object from the STR book library, this stobj3, and in fact we're going to shorten this to only look at the July temperature. So I'm going to do this operation here to create stobj4, and let me run line 147. This stobj4 R object is of class STFDF. So this is a specific type of class designed to work with space-time data. You can see that what we have is we've got a bunch of, if I look at the attributes of this object, it has something called time. So we're going to be looking at the times in July. It's got locations. So here are the spatial points. This gives us the locations of all of our points. And then the data is stored in this thing here. So this is just a specific format for the to work with the tools for this space-time library that goes along with the book. And rather than spend the time working our residuals into that format, let's just do this, work with this data set. So We're going to use this tool called variogram. This is slightly different than the variog tool we used in GOR because it's going to do space-time. Let me, this is actually not what I want here. You put STJ4. Hopefully this is going to work. So I'm going to run this variogram. It's going to look for the Tmax variable. In here, well, let's run this and see if it works. I'm afraid I may have messed something up. I think we might be okay. Hold on just a second. I'm doing something offline here. Shoot. Okay, I'm gonna have to make a correction here. I'm gonna pause the recording. Okay, I think I've got it corrected. So let me share my R screen again. I had messed with something. Our data is stored in the STOBJ4 object. Notice what we're going to do is we're going to, our variable, this Z is the temperature. We've got the squiggle 1 plus lat. So what we're doing is we're regressing on latitude. So we're trying to remove that north-south trend. And you'll recall that what we did here, or what really Weichel and authors did, was they looked at just the July data. So they're trying to remove the mean in time, which we before fit with a quadratic function. By looking at just July, they're saying they pretty much removed the seasonality. This is useful at least for demonstrating this procedure. So it's running that variogram, and now when I plot VV, here's what I get. And so notice that this is like that plot that I was trying to describe before. In the horizontal direction is the spatial distance. In the vertical direction is time lag. What we're seeing is that for far enough spatial distance and large enough time lag, we're maxing out at about 20 to 25. So our SIL is 20 to 25, maybe 22. Down here at spatial distance 0 and time lag 0, we're getting basically an estimate of 0. We are seeing things increase with spatial distance at time lag 0, and then at time lag 1, we're already seeing quite a difference. So that that average difference, even at lag 0, but at spatial lag 0, temporal lag 1, we're seeing that on average, the squared difference between the Z values is at about 10. And so that's that jump that we saw at lag 1. And so this gives us some kind of visual representation for how the spatial and temporal structure behaves. Let me say one more thing. So a lot of the focus in Monday's lecture was on separability. And we said that a model was going to be easier to model if it was separable, but if it's but many processes, a separability is an oversimplification. It wouldn't capture the kind of phenomena of moving weather or something like that. What this gridded variogram, the space-time variogram gives us is a method to basically a diagnostic method for testing for separability. So what we have in our grid are estimates of gamma hat as a function of H and K. If it were separable, any of these cells would be the product of a spatial process and an independent temporal process. So what we could do basically is we could, if we could convert these variogram values to covariance function values, then we could see if these cells appear to be the product of our marginal behavior in H and K. And so that's what I'm describing very briefly down here. We know that our variogram is C0 minus CHK. So if I move the C0 over to the other side, I could say C0 minus gamma HK equals C of HK. So if I take C0, the variance, our SIL value, basically 22, 23, subtract our gridded values from 22, 23, what I'm going to get are estimates of the space-time covariance function. And then what I could do is I could take the spatial only covariance function, the covariance function evaluated at lag 0. I could take the temporal covariance function, so that's evaluated at lag 0, and I could see if the pattern, the colors of our estimated covariance function looks like the product of this times that. So you can imagine getting these values, getting those values, making a grid of their products, and then comparing those grids to see if there is evidence for non-separability, or maybe a better way of saying it is for not having symmetric behavior in the covariance function. So that's what I'm saying down here. Does our grid of values appear to equal the spatial covariance function times the temporal covariance function? All right, that's all I've got for now. I am hoping to, we will see if there's, I need to do a little bit more exploration of space-time topics and see if there's anything I want to add to the lectures. So that's where things stand as of right now. It's 5 o'clock on Monday evening. See ya.